So, hello everyone, this is SDB, and as I promised, I will provide the solutions of those problems which are not manageable by people to understand. And I will explain this in this video because someone on LinkedIn commented that he or she don't understand some of the steps in my solution, which is quite eligible because which is quite legit because sorry for my bad English, which is quite legit because I skipped some of the steps, which is correct. I thought you guys will understand, but it's not that the case because yes, it's my fault because I skipped some of the steps. So let me explain the problem. So those of you who don't know which problem I'm going to explain, so CMI 2006 Integration Bee round 3P9. Okay. And those who don't know what CMI is, CMI is Chennai Mathematical Institute, which is one of the premier mathematical institute in India. I mean, one of the best institute in mathematics in India. And this solution is by me, as you see, STB, that is Safal Das Biswas. And so let's proceed to the problem. Okay. Okay. Let's proceed to the problem. Okay. So here is a view of this problem. So let phi n denotes the number of positive integer lesser than equals to n and co-prime to n, where n is a positive integer. And that means phi n is a Euler-Tochian function, those you know, although I will explain those who don't know, but phi n is a Euler-Tochian function. And let this notation for x denote the GIF of x, that is greatest integer function. Denotes the largest integer lesser than equals to x, where x is a real number. That means, for example, box of 1.5 is 1. I mean, okay, box of 2.5 is 2. I mean, box of 2.2 is also 2. I mean, box of what is box of pi? Box of pi is 3 because pi 3.14 something dot dot dot. So, box of, that means greatest integer lesser than equals to pi is 3, right? Okay, that's it. That's the explanation of box function. Okay. And before explaining this video, I will say that my handwriting is not that good while I'm on graphic tablet, so spare me on that. And what I want to tell you guys that please keep track on the line where I'm writing. I mean, please keep track on my pen, right? Because if you don't track on my pen, you will lose the focus. And please also follow the words I'm saying while recording this video, right? Okay, that's it. That's what I wanted to tell before beginning the problem. And so here is the problem, as I said, up to real number. So it's asked to compute the integral 1 to infinite phi of float of x by float of x. Okay, so another thing, I will restrict saying GIF of x as float of x, okay, in the video. It means GI of f of x, I will say it float of x while mentioning the problem, while detailing the problem in the video, right? Okay. So integral 1 to infinity phi of float of x by float x cube dx. That means phi of GIF of x by g of divided by that means phi of x over phi of GIF of x over float of, I mean, GIF of x cube, that is a float of x cube dx, right? So let's solve the problem without much delay. So before beginning the solution, I need few definitions to tell you guys. So what are those definitions? Definitions are this. That means an arithmetical function f into c is said to be multiplicative. That means, now this is a fancy word, that is arithmetical function. So you people might get confused what is arithmetical function, but there is no reason for of being confused because arithmetical function is actually a function that maps the set of natural numbers. Okay, so this is a notation for set of natural numbers I am using, and I will take the natural numbers from 1, 2, 3, 4, and so on. So if set of natural numbers to the set of complex numbers, So this type of functions is called arithmetical functions, right? So this type of functions are called arithmetical functions, and more specifically, we said it to be multiplicative if the following conditions hold. That means, yeah, if we take two natural numbers mn such that they are co-prime, that means the GCD of mn is 1, then we say that f of mn is f of n times f of n for all mn belongs to n, and we need another restriction, that is f of 1 equals to 1, right? So f of mn is f of m times f of n for all mn belongs to n, and given GCD mn equals to 1, then we say the function, this arithmetical function, is multiplicative. And another restriction to consider the multiplicativity is f of 1 equals to 1. Now, those who don't know what is GCD of Mn, this GCD of Mn is simply HCF of Mn, the highest common factor between the two natural numbers m and n. For example, if you take m equals to 1 and n equals to 2, those are natural numbers, obviously, because I said I will take natural numbers from 1, 2, 3, and so on. So, given GCD mn equals to 1, that means GCD of 1, comma 2 is 1, and GCD of 2, comma 4 is 2, because the highest common factor between 2 and 4 is 2. And that means that simply HCF, those who are confused about what GCD is, right? That means the greatest common divisor between m and n. Okay, that's clear. So, sorry, excuse me. Example, Euler-Toscan function. Euler-Toscan function, that means the function we have started with, and I have told you in the question, that function is one of the multiplicative function in the class of multiplicative function, right? Okay, so denote the number of positive integer lesser than equals to n and co-prime to n, where n is a positive integer. Okay, that's define the Euler-Toscan function. That means phi of x actually counts the number of integers that are lesser than equals to n, and they are positive natural number. That means the natural number, according to my definition, I'm restricting here. That means we are restricting all positive natural number lesser than equals to m, such that those natural number with n shares GCD1. That means if you take a number lesser than equals to n, say a, we say that phi x counts that a if GCD of a comma n equals to 1. Got it? Okay. For example, what I can say, what is phi of 6? Okay, so phi of 6 is actually, if you count 1, so one is one of the one is in every, I mean, in every phi of x you need to count one, because one always shares a GCD 1 with n, right? Okay, so phi of 6 is actually all numbers less than equals to 6 that shares GCD 1 with 6. That means 1 and 2 is not there, right? Okay, yeah, 3 is also not there, because 2 and 6 has GCD 2 and 3 and 6 has GCD 3, right? And so that means that one counts in phi x, and the next number is just 5, because 1, 2, 3, and 4. If you take 4 and 6, that's also shared GCD 2, but that's not in the definition of phi x, right? And in the definition of phi x, we need just GCD to be 1. That means 1, and the next number is 5. Thus, phi of 6 is just 2. And you can see that phi of 2 is 1, and phi of 3 is what? Phi of 3 is 2. That means phi of 6 is just phi of 2 into phi of 3. And the amazing part is phi of 2 and 3 has GCD 1. And you can see the definition of multiplicative function is verified, right? Because phi of 6 is just phi of 2 into phi of 3. So this is one of the example. Fine. So, phi x is not the only multiplicative function. There are many multiplicative functions. I'm not getting into that. But there are a lot more, as I have written, you can see on the screen that there are a lot more such functions, but we will not cover all those in this session because it will be long, right? So another theorem I just need to explain the problems, fundamental theorem of arithmetic, and this is one of the very key theorem in number theory. I mean, this is one of the, as you see, fundamental. This is one of the building fundamentals. You will see this problem while you see this theorem while you're in the fundamental of number theory. I mean, in the very beginning of number theory. These things are basis. I mean, these things are the very basic thing you need in number theory, right? So it states that every positive integer n greater than 1 can be written as the product of prime powers in a unique way up to the orders of the product of prime powers appears in it. What's that actually means? Okay, This is not that very critical to understand, but what it actually means is if you, so what is prime? You obviously we all know it. So a prime number p is a number which whose only positive divisor is 1 and p, right? Okay. Where p is an integer, obviously. Okay. Then we say it's a prime number. Okay. So, what are prime powers? So, if you take a prime number p and you lift it, I mean, if you raised that prime, that means if you raise the exponent, I mean, if you take p to the power alpha, that means p raised to the power alpha, and alpha is an integer. Then we for a prime number p, if you take a prime number p and raised it to the power some integer alpha, positive integer obviously. So if you take a prime number p and raise to the power a positive integer alpha, then we say that this is a prime power, right? Okay. The proof uses strong induction. So I will cover a small sketch of the proof, but I will left the uniqueness part to the viewers or readers, because the uniqueness part is not that critical if you have understand what is going on. I mean, you need to show the uniqueness by taking two different representation. That's it, nothing else. And the example is 120. For example, 120 is a positive integer and we want to factors it in prime powers, right? So, okay, so I want to tell another thing, that one is not prime in our, one is not prime. So we don't consider one to be a prime number. And why so? Because you will understand this if you have gone through the code of number theory, because while defining tau functions and I mean, the basic part is tau function. So while defining tau function that counts the number of positive divisors, we need to restrict one to not to be a prime. So uh, unless that will not give a valid reason to consider tau function. And that can be one of the vague or loosely we can say why one is not prime. So that's it. And 120, so 120 is 2 cube into 3 into 5. Okay, so 2 is a prime, 3 is a prime, and 5 is a prime, and 2 to the power 3 is a prime power because 3 is a positive integer. So 2 to the power 3 is a prime power. Also 3 is a prime power because 3 to the power 1 and 3 to the power 1 is just 3. So 3 is a prime power. Same for 5. 13 is 13 to the power 1, and you can see that 13 to the power 1 is a prime power. And 1024 is 2 to the power 10, which is again a prime power because 10 is a positive integer and 2 to the power 10 is just, and 2 is prime. So 2 to the power 10 is a positive integer. And 3, 4, 3 is 7q. You can see 7 is prime and 3 is a positive integer. So 7 to the power 3 is prime. And you can see, so one of the thing to note in prime powers that 2 to the power 10 is a prime power. That's okay. But this 10, you may get confused. Many people get confused. So prime powers means this 10 should be prime. No, in prime powers, we are not restricting that alpha, I mean b to the power alpha, that alpha may or may not be a prime integer, prime positive integer. May or may not be a prime positive integer. That means alpha is just a positive integer, not prime, right? So in prime powers, we just need that p, that means the base, that means the just p, that base to be prime, but the exponent may or may not be prime, right? That's it. So we are proceeding to the next part of our lecture session. So, so in this session, as I promised, I will give the proof of, and I'm moving to my graphic tablet. So please follow my pen and track my pen. And I mean, my handwriting may get bad. I will try my best to keep my handwriting good. And the next thing is follow my words, okay, properly, unless you will not understand the video. Okay. So, fundamental theorem of arithmetic uses, I mean, okay, sorry. Okay. Oh, sorry. Okay. Okay, sorry. Oh, wait. I got a glitch. Where is F5? Okay. 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 So fundamental theorem of arithmetic, I'm going to explain. It uses strong induction. Now, a bit what is a strong induction? Those who don't know, so in strong induction, we consider all the numbers. I mean, I am taking all the numbers still in. all natural numbers, and so on. In strong induction, we actually prove the statement for one, for maybe one, or okay, so let's prove the statement. Oh, okay, not one. So okay, maybe one, or maybe two, or maybe three, whatever our base case is. For example, in strong induction, we prove the statement of the base number, right? So in strong induction, we prove the statement for the base number. Then we assume it is true for all number less than equals to n minus 1. Suppose the base number is b, say, then we assume it is true for all number x less than equals to n minus 1. And then with this information, suppose the statement is true for base number and assume it's true for all x belongs to all x belongs to n and less than equals to n minus 1. Suppose it's true for all x less than equals to n minus 1 and all x belongs to n, and trying to prove n, the statement for n, right? And this is the idea of strong induction. In induction, what we actually do, we prove for base. In first principle, we prove for base, then we assume it's true for n minus 1. And using this n minus 1, we proved for n, right? That means the map is base goes to n minus 1 goes to n, right? This is the map in first principle. In first principle, right? In first principle, this is the map. That means we prove for base, then we go to n minus 1, then we go to n. But in second principle, what we did is base to all numbers between b n minus 1 intersect with n and then go to n. I hope you understand. I mean, we assume all numbers. This is true for base and all numbers between them and then go to n, right? This is the second principle of induction. Nothing fancy, I mean. Nothing fancy, right? Okay. So, how to prove fundamental theorem of arithmetic? Fundamental theorem of arithmetic, just a sketch. Nothing. You just 2 is a prime power, right? 2 is a prime power because 2 is a prime and 1 is a positive integer, right? So the base case, because n greater than 1 is not prime. And in theorem, we assume n is greater than 1, right? So, okay. So 2 to the power 1. And we assume it's true for 2 to the power, it's true for 2. That means 2 is a base case now. So suppose it's true for all numbers. So we are going to the next step. X less than equals to n minus 1, right? So this is assumption of induction. Now suppose we consider n. If n is a prime number, then we are done, right? If n is a prime number, then done, right? If n is a composite number, then we need to get back to the definition of composite number. That means in a number is composite if it is written as a into b, where a, b are positive integer, where a greater than 1 and b greater than 1. A greater than 1 and b greater than 1, right? So n is a composite number now because n is not prime, right? So there are two integers a and b such that a greater than 1 and b greater than 1, right? Okay. N is a composite number. You can also do by dividing by that prime. I mean, if n is not, if n is not prime, then I mean I am using the definition of composite number here. I mean you can avoid this definition by allowing that if p is a prime, then p divides n. If n is not prime, then p divides n. Then you can consider the number m by p, and n by p is an integer, and you can express this as this is a smaller number less than n, so this is lesser than equals to This is less than n, and n by p is actually less than equals to n minus 1, so it can be written as a product of prime powers by definition. So that's it. So you can do this, but I am using the definition of composite number, so because it will be helpful for me to use the definition of composite number for the following. So but this is see, because I'm talking it loosely. So if so n is a composite number, so n can be written as a product of two integers a and b, so a greater than 1, b greater than 1. So n by a is an integer b, right? And b is less than equals to n minus 1. Why so? Because n equals to ab and a is greater than 1, so this is greater than equals to 2 times b, because a is greater than equals to 1, and so n by b. Okay, let me n by 2 is greater than equals to b, which is obviously lesser than equals to n minus 1. Similarly, we can show by the same reasoning that n minus 1 is greater than equals to a. So what we have proved, that is, so I'm backing my this here, so I will follow up from here. So we have that n by 2 greater than equals to a, and n by 2 greater than equals to b, right? Now, A and B, the problem is true. Why? Because this is lesser than equals to n minus 1, and this is lesser than equals to n minus 1, right? So this two thing, the problem is true by our assumption. So A and B has a prime power factorization by induction hypothesis, and that means n equals to AB can be written as the product of prime powers, because A can be written as the product of prime powers by assumption, and B can be written as the product of prime powers by assumption. Now, clubbing, if there is any common between them, that means if there is any common prime between A and B, we can club those and take the product and take the addition in their exponent, because we know that k to the power m into k to the power n is just k to the power m plus n. So p, if there is any common prime, then we can actually take, if there is any common prime, I mean, if there is any common prime between a, then p to the power that p to the power some that exponent alpha and beta. That means if p to the power alpha, if p to the power alpha fully divides a, what is fully divides? That means p to the power alpha plus 1 does not divide a, but p to the power alpha p to the power alpha divides a, but p to the power alpha 1 doesn't. So p to the power alpha fully divides a, and p to the power b beta fully divides b. Then we can actually club those product, and we can get again a prime power, right? So, and this proves that theorem, right? And so another way to prove the theorem is also using strong induction. But as I said, I have used the definition of composite number, but that doesn't use. You just take a product of primes, and not by using powers now, but you can take the primes. I mean, just take n equals to p1, p2, pk. I mean, p1, p2 can appear more than once. I mean, p can appear, I mean, a particular prime can appear in p1, p2 up to pk more than once. I mean, this can be written as some p to the power alpha 1, q to the power alpha 2, where p and q are prime. So if you let like this, and then divide by a prime, then you can actually see that this is smaller than equals to n minus 1, and you can repeat the strong induction. That's it. I mean, this can also be done, but I am using the definition of composite, nothing else, nothing fancy. That's it. And so moving forward, so I hope you people get what is strong induction and how to prove fundamental theorem of arithmetic. That's it. And going to the next slide. So this is one of the very good expression what number theorist can achieve about phi n. This expression, I mean, phi n can be written as n times the product of p divides n times 1 minus 1 by p, right? And this is the product notation, right? I hope you know it while you are in this stage of watching this video. What is product? So phi n is actually n into product of p divides n, all prime that divides n, times 1 minus 1 by p. So a short explanation how to prove it. So if you take all the numbers till 1 to n, right? So so I am assuming that n is greater than equals to, I mean, okay, you don't need to assume it. So suppose you take a prime p that divides n, right? So the number of so if you take so n equals some pk, right? So the probability you choose the number, I mean, the if you take a number, random number from this set, the probability that that number is divisible by p is just 1 by p. Why? Because the number of integers in this set that is divisible by p is just k by n, right? I mean, k is the number of integers that is divisible by p. And we know that where k is this k. And we know that why? Because n is equals to pk. So p, 2p, 3p, up to, you can go up to kp, right? So this is the number. So one, so you can take one from here, one another from here, and another from here. So 1, 2, 3. So there are k integers. So k by p, k by n, right? So k by p, k, and this is just 1 by p, right? So an integer from this set, so if you take an integer from this set that is divisible by that prime p, it has probability 1 by p. And so if you take the complement, that is 1 minus 1 by p is the number of chances that p does not divide any or I mean divisible by p. So this is the number of this is the chance that p does not divide any of this integer. This is the probability that p does not divide a particular number from this set. So, and we want the, so if you take this and you do the product for all prime p that divides n, so this is the probability that an this gives the probability that an integer in this set is co-prime to n, right? Because we are actually I mean, we are actually eliminating all the prime divisors, I mean all the prime that divide n from, I mean, after, so p does not divide any of this number. I mean, p, if p is a prime factor that divides, and p does not divide I mean, p does not divide any of this. I mean, if you take a particular number, so this give the choice that p does not divide that number, right? And we want this to happen for all primes, right? And this means that this gives the probability that uh, this is the probability that n lesser than equals to x, and x lesser than equals to n, sorry, this is the probability greater than okay, let me erase it. So this is the probability that 1 lesser than equals to x lesser than equals to n, and gcd x comma n equals to 1, right? Okay. And this is just by definition of phi n, this is just phi n by n. And if you just multiply it here, the n, you will get the desired result. That means this result. Fine. So, and from, if you, from this result, if you just plug, I mean, so phi of p is just p times product over, I mean, product over p divides p 1 minus 1 by p, which is just p into 1 minus p by p, which is actually p into 1 p minus 1 by p, and p cancels, so it's just p minus 1, right? And also you can actually prove this result by applying this formula and using the fact that just gcd mn equals to 1 here. How to do so? So if you just take product, I mean, I am actually writing this here, right? So if you just take product p divide mn 1 minus 1 by p times mn mn mn, then this is actually m times product, this is equals to m times product q divide m 1 minus 1 by q, because the GCD is 1, so they share no common factor, right? Keep this in mind. So this is n product over p divide n 1 minus 1 by p, and luckily this is just phi m and this is just phi n, So this is the product. So we proved that this identity, right? And why is this is happening? Because the GCD is 1. Because we know Mn equals to LCM Mn into GCD Mn. So this is just 1. So this Mn is just M into N, and this is just 1. Right? Okay. So Mn is just LCM Mn because GCD is 1. And so we can write M and N just have distinct prime factors. So M and N has just distinct prime factors. So this prime Q is distinct from all the this prime space. Right, and that's it, and that's it. That's it. I mean, this is not critical. And if you just plug p to the power alpha a prime power, you just get this formula. Right, and that's it. This is not that critical. Okay, now proceeding to the next. So this is one of the very important thing about So, okay, guys, I'm back again. Sorry for my computer glitch and my recording issue. So, let's back to my problem. So, to the problem. Define Riemann zeta function for all real numbers s greater than 1 by zeta s equals to 1 summation k runs from 1 to infinity 1 by k to the power s, which is convergent, which is proven to be convergent for all s greater than 1. Now, I'm not giving the proof of the convergence, but this convergence can be proven just by taking some real analysis facts, and you can use, I have given the hint in the video that you can actually use powers of 2 while proving the using the reciprocals of powers of 2. uh, you can actually prove the convergence of Riemann zeta function for all s greater than 1. And note, I'm not using any kind of complex extension of this Riemann zeta function. I'm just defining this Riemann zeta function for all real number s greater than 1. I'm not giving any complex extension. There are, but I'm not giving because we don't need this complex extensions of Riemann zeta function for this particular problem. That's it. So I need a very cool fact about Riemann zeta function. Those of you who knows about this prime factorize prime expansion of this Riemann zeta function, that's perfectly fine. But I'm going a bit about that. So Riemann zeta function is just actually zeta s plus 1 plus summation 1 by k to the power s. K runs from 2 to infinity, right? And we have proven the fundamental theorem of arithmetic, right? So this is just 1 plus summation beta, I mean, why, okay, so you just take one product over b to the power beta, and the ranges is beta belongs to integer union 0, and all prime p belongs to p, right? I mean, this is the expression. I mean, this set we need to run this summation and product, right? I mean, okay, that's it. So if because every integer can be expressed as the product of prime powers, right? And you can take any natural number and you can take every positive integer, so you get the expansion like this, because this is okay. So beta to the power s. So if you take this sum and take this product and over primes and over all beta belongs to natural number union 0, you will get every every factorization. I mean every integer. I mean you can cover all these integers, right? And if you just look at this, I mean I mean just delete this one. You don't need to need the one because you are allowing this 0 here. Okay, so you can take 0 0 0 0 0 and that will be just 1. So this is actually just okay. What? This is actually just product over summation 1 by p to the power 1 by p to the power ks. K runs from 0 to infinite and p belongs to p. right? So we don't need the one. I have mistakenly written one, but we don't need to rewrite that one because one is covered here also. Because if you take all the exponent to be zero, that is one. Oh, okay. So I forget to explain one of the things. So one of the user is asking that product. One of my not user. I mean one of the LinkedIn user is asking that product over one and p belongs to p is divergent. No, it's not. It's not divergent. It's just one. Why is that one? Because if you just take a n to be the product over 1 over all prime numbers, that is lesser than equals to n greater than equals to 1, right? You are taking this product p belongs to p, so you will just get 1. And this is true for every natural number. In other words, limit n tends to infinity, a n equals to 1, right? So this is one of the doubt of the one of the LinkedIn user. So this is cleared, I hope. I mean, you just actually, what is actually we are doing is you just take a n equals to the product of this over all primes, and you just get 1, right? Because it's a finite product. And this is true for every n, every prime lesser than every n, right? If you take all the primes lesser than equals to n, and this is true for every n, so this should be 1, right? So this is true for every n. So taking so you just take a1 equals to 1, a2 equals to 1. So the sequence is just 1. So you just take limit n tends to infinity. So it's again 1. So the limit should be 1, right? I hope it's clear. So this idea, you can actually think it here, because we are actually taking product over primes and 0. So we are actually allowing p to the power 0 for all p belongs to p, while taking, so this is actually 1, because this sum actually takes care of that one, while this is actually happening, and this thing is actually happening because of this one. Okay, so this is actually this, and this is actually just what? Product over 1 minus 1 by p to the power s whole to the power minus 1, right? Where p belongs to e. Sorry for being funny in my sound. That's okay. Sometimes it's cool to be funny while doing maths, unless it get bored. And so product over p belongs to p, 1 minus 1 by p to the power s to the power minus 1. This is just geometric series, right? We everyone know this is just a class 5 thing, right? Okay. Okay, I'm just kidding. This is from class 11, but standard 11. Not class means standard 11. But those who like maths, I think they already have done in class 7 or 8 or so. Okay, that's it. That's it. I mean, this is it. That means zeta s is actually product p belongs to p, 1 minus 1 by p to the power s whole to the power minus 1, right? That's it. That's the expression for zeta s using prime numbers, and that's it, nothing else. That's the thing we need for this problem. And I'm proceeding to the next. So this is the main thing. This identity is needed in proving that problem. This identity is actually needed. So what is this identity? So this says that this is actually zeta 2 into zeta 3. Okay, before proceeding, I didn't provide the proof of zeta 2 equals to pi square by 6. This value is a very known value. However, zeta 3 is known to be convergent, and it has a finite value, but we don't know what is the exact proper closed form of zeta 3. Okay, by the way, the zeta 3 may not be known with a proper good way of lookup, but zeta 2 is known to be pi square by 6. And those who know Fourier analysis, I mean, one of my favorite proof of zeta 2 equals to pi square by 6 uses Fourier analysis. Those of you who knows it, perfectly fine, but you don't need to require to know the proof. Just keep in mind that zeta 2 equals to pi square by 6. That's it. You just need this. But to prove this, you will try proving it if you know Fourier analysis. This can be proven using complex analysis also. But complex analysis idea is basically near to the idea of Fourier analysis. I mean, harmonic analysis or Fourier analysis. I mean, yeah. Fourier theory. Or American analysis. So this zeta 2 equals to pi square by 6 can be using Fourier analysis, and that's it. So this identity is true, and why this is true? So let me prove it. Why believe me, man? Why to believe me? Let me prove it. So let's SDB show it, unless world will not accept it. Okay, so zeta S is actually product over 1 minus 1 by p to the power S whole to the power minus 1, right? P belongs to P, right? So let's see what is zeta 2. Zeta 2 is actually product 1 minus 1 by P to the power 2 whole to the power minus 1. P belongs to P. And zeta 3 is just product over P belongs to P 1 minus 1 by P cube whole to the power minus 1, right? Okay, so zeta 2 by zeta 3 is just product over P belongs to P. I'm just taking the reciprocal. Don't worry, don't mess up here, you guys, okay? I'm keeping a step jump. I hope you get this. Okay, why? Because zeta 2 is reciprocal of this, right? And zeta 2 is up here, and this is reciprocal of this, right? So zeta 2 is just 1 by p to the power s, and this is zeta 3 is here, so zeta 3 is reciprocal of this, so it will go up, right? So this is actually product pq minus 1 by pq into sorry for that sound, into p square by p square minus 1, right? And this is actually product p belongs to p, this p cube and p square cancel, so p cube minus 1 by p into p square minus 1, right? And this is actually equals to product p belongs to p. Okay, so p square plus p plus 1 by p into p plus 1, right? And this is actually product p belongs to p, 1 plus 1 by p into p plus 1. So we have proven that this expression is actually equals to this expression, right? And this is expression is just this, right? That's it. Nothing fancy, right? This is it. Okay. So that's it. Nothing else. Okay. So you get the proof, right? Now every setup is done now. Okay. So every setup, I mean, I did every setup for this problem, right? Now I just need another thing. So I will explain that in the further coming up slide. Okay. Okay. Visit here. So you have seen that I have written this expression, right? Am I written this? Yes, I have written this. This expression, I have written this. This expression is nothing but phi is multiplicative, bro. 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 Phi is multiplicative, bro. Bro says bro. So this phi is multiplicative. So you have remembered that I have written summation, product, that type of thing, right? This is just the same thing. I mean, just reorder it. I mean, summation, product, or product summation, just reorder it. Okay. Okay. Summation, product, just reordered it. And nothing fancy. Okay. I just reordered. Okay. Wait. Okay. Okay, yes, okay. Okay, some product. So phi is okay. Okay, so leave it. So phi is multiplicative, right? We know that p to the power alpha 1, p to the power alpha 2, and so on. P to the power alpha k is just phi of p to the power alpha 1 dot, 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 phi of p to the power alpha k, right? So in the zeta function, if you have remembered, I have used that this notation. So, okay. Wait, guys. So this is just minus, right? This is just minus. Sorry, I'm sorry. I'm sorry, because this is the reciprocal. This is the reciprocal. Okay, guys. So, have mistaken. I have mistaken. So I have mistaken that. So this product reviewer, this is minus. This, I mean, 1 by p to the power something. So this mistake I have done before. So check on it. So I just, I mean, I'm lucky to revisit this slide. I just saw it. So this mistake I have did. So just look over it. So this is just this and this. Okay. So if you just allow instead of one phi, is there anything changing? Yes, changing is this phi to the power phi of k. This is just going to add because this is multiplicative, right? I mean, this, in this, I mean, if you just take this expression, ms equals to summation k runs from 1 to infinity p to the power a k to the power s. This is just summation beta belongs to n union 0, p belongs to p, product, what? Product, times phi p to the power what? What? Okay, okay. So p to the power some beta s by b to the power beta s, or I'm mistaking something. P to the power beta. Wait. No. Why beta is just beta? P to the power beta s. Okay, so this type of thing is coming. Let me explain it properly. Okay, let me explain it properly. So, so let me explain it properly. Oh, give me some space, bro. Okay, so let me explain it here. So if you define a function m is equals to summation 1 by k to the power s phi of k, right? And k runs from 1 to infinite. And this means we can actually prime factorize it, right? So this is actually product summation beta belongs to 0 union n product 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 is over prime and beta is over okay, so anything. So p, where p to the power minus k is minus yk man y beta is into phi of p to the power beta, right? This is simple, right? I mean, this is actually happening, right? And this is actually equals to, okay, phi of p to the power beta, right? Okay, phi of p to the power phi of p to the power beta, beta is splitting. Yeah. So this is actually equals to this. This is actually equals to summation, just simply summation. This product where product the summation phi of p to the power r by p to the power rs into r runs from 0 to infinite, where p belongs to p. This expression is actually equals to this. Okay, same argument as this. Same argument as this, nothing else. So be aware this minus 1. So okay, same argument as this. Same argument as this, and that's it. So and so that's it. I mean, you just split the betas and that's it. So nothing fancy, and so that's it. Okay, I mean, this, and that's it. I mean, okay. So, okay, let me explain. So this is beta zero union and P belongs to P beta 1 minus phi beta, because this is happening because phi of P1 alpha 1 where P1 dot Pk alpha Kr primes. This is actually equals to phi of P1 alpha 1 dot Pk phi K of alpha K, where this is true. This is equals to, because where P1, P2, and so on, Pk are primes. Okay, that's it. And this is the setup. And I'm to the end of the video. And so this allows me to write this expression to be this. And from this, just compute this, because we know that this phi of p to the power k is p to the power k minus 1 into p minus 1, because it's here, and that's it. Just compute it, plug it, use geometric formula, you will get this, and we have derived the identity 1 plus 1 by p plus p into p plus 1. And this expression is actually, if you just compute this expression, this is this, and just this expression is just this, and you just plug over all prime. This is zeta 2 by zeta 3, and this zeta 2 is pi square by 6 by zeta 3, and that's it. That's it, and that ends proof. So final remark. Thanks for watching. As usual, for a new start in the YouTube, I must say like, share, and subscribe. And hope you learned something from this video. Sorry for the grammar. And hope you learned something from this video, and keep commenting on my posts and videos. And if you have any doubt, let me know. You may be on LinkedIn, you may be on Instagram, you may be on Facebook, anywhere you are. Just keep the right track to chase me if you want to know something from me about the solutions I post, or you have some query about a problem, just, I mean, solvable problem, right? I'm not saying about conjecture, because I am already on a conjecture which I have not solved yet. So don't post conjectures. Just give solvable problems which is possible for a human to solve, or for AI to solve, maybe, because okay, nowadays AI is very famous, which is possible for a human to solve. So let me know if you have any doubt, so I will try my best to solve. That's it. So like, share, and subscribe, and spread this video if you like it. And I hope you learned something from this video, and keep commenting on my posts and videos. Bye bye, sayonara. And already you have seen this is me. So the on the whole video you can see my face here. And this is me. So that's it. Thank you, and bye bye. So ta-da.